My name is Jenny Barmier, and this is the fourth video in a series of ship stability. We're going to discuss in this presentation and this video how we obtain the stability equation for rectangular. In this case, we have the rectangle and we have the dimension of the rectangle. The dimension of the rectangle is b, it's the width of it, s is the length of it, and d is the height of it, and small d is the amount of the material that is immersed in the water or in the liquid. The governing equation is the difference between g to b, and it has to be smaller between the moment of inertia to the volume. The moment of inertia is typical thing that can be calculated for area. It's the area of this gray shape that is given here. For a rectangle shape, it's S BQ divided by 12, and the volume that is submerged volume is D times S times B, which is very clear. And as I said before, the gravity center is big D divided by 2, and the buoyancy center is small d divided by B. And if you utilize Archimedes principle, we can obtain the stability equation. If you want to go for the detail, you can go and find it in my book, Ship Stability and Other Body. It's free on Poto Project. And if you try to draw this diagram, you will going to get this curve showing the location of the stability. It will be in the middle. There is some kind of dome, that under the dome the body is not stable, and above the dome is stable. The x-coordinate showing the ratio of the density, while the y-coordinate showing the width of the object times the height of the object. And if it's very wide, it will be stable, and if it's very narrow, like small amount, in fact, just as a curiosity or a curious point, we'd like to mention that most of the ships today, they are about 0.1 or 0.8, and ship like Evergreen, the ship that blocked the Suez Canal, almost all the ship that is today in usage all over the ocean, all over the world, they are mostly unstable in water, and therefore they have to have the gravity center lower to decrease the typical size of it. So to summarize what we show, we didn't really use in this analysis any imaginary point, like we will be talking about it later on, a point like metacenter, and that's the typical analysis was done. There's no such imaginary point or line or thing like this. It's very clear, showing what's going on. The presentation is of this analysis also in dimensional form, so we don't going to give you a dimension that you don't know if it's big or small or relative. It's all precise and showing location where it is unstable, so it's in dimensionless form. And dimensionless form, it's encompass a lot of information in very brief way to do it. And the explanation of the physics is very clear. You can clearly see where is stable, where it's not, and what to do in order to get it stable. So if you are in a small boat and the boat is showing to you a sign that it's very unstable, what you should do in order to make it more stable. If it's on the left-hand side of the dome, you will throw things away, and if it's on the right-hand side of the dome, you add weight to the boat to make it more stable. I hope you enjoyed the video. Thank you very much for watching it. Please click like, subscribe the channel, and leave a comment if you have any question or if you just like it.